In sections 4.1 and 4.2 of our 301 workbook involves continuing to apply the concept of mesh currents to find desirable voltages or currents with resistances in a more complex topology. But this time we're looking at when current sources themselves are in the network, or even sources that are controlled by other currents or voltages in the circuit. And how can that help us resolve equations using the mesh currents a little bit in a little bit more easier way. One thing to realize though is where certainly current sources force a specific current to flow through its terminals onto the rest of the circuit, the voltage across the terminals of a current source is not predetermined, okay? So that would depend on what would the voltage that's available from from other parts of the circuit. So it's a common mistake to assume that the voltage across the current source is zero. That is not true. There is voltage across it, okay? So let's look at an example where we're using mesh currents, but there is a current source also in the circuit. So in this case, example 14, which actually is at the bottom of page 62, but I've kind of put the top of page 63 just below it so that I don't have to redraw the circuit. And we can do our work in this box on the top of page 63. So notice in this case that we have a planar network, certainly. And this case, we can see we've got two closed paths there. And so we have two mesh currents indicated. And of course, our convention, as we mentioned in the previous lecture, is that the convention is to draw the mesh currents clockwise. But the interesting issue here is that we already have a current source available for that current. So, so immediately, what we can conclude is that, again, if we're just looking at this mesh completely independent of the other one, which is the idea, then the current that's actually flowing in this series of two resistances of 15 ohms and 10 ohms is in fact 2 amps. So in this case, if you have defined the mesh current, but you have a current source within that mesh, in this case, by definition, this is just 2 amps. It's as simple as that, okay? And that's only because you have a current source there, all right? And so if we wanted to, in this case, we want to, we know that I sub A is 2A. We want to figure out what I sub 2 is via a Kvl equation on mesh 2. So that's our goal, is to figure out what the current is on the other side, right? So let's do our Kvl mesh 2 equation. And again, we're trying to represent voltages using our mesh currents. And of course, the idea is, in representing the voltages, we have to look at multiplying the resistance by the differential in the mesh currents. In this case, we assume PRC, of course, coming through with I2, but an opposing current represented here as I1 is opposing it. So we would write that voltage as I2 minus I1. Because we are in mesh 2, it'll always be that subscript minus the other, the external current represented from some other mesh, okay? That's pretty much the way we look at it, all right? And then, of course, if we look at the other resistances in that part of the circuit, you would have 5 ohms times the mesh current I2, and then you're coming into the positive polarity of the 10-volt source, that's plus 10, and that has to be equal to 0. And so then very quickly, we can collect some terms here and show just algebraically, it won't be hard to see, you're going to have 15 I2, and you will have minus 10 I1, and that's going to have to be equal to minus 10. We pull that, that scalar 10 to the other side, okay? But we already know from having that current source over there, which must be the same as the mesh current I1, then we can substitute that in for I1. And so that implies that 15 times I2 minus 10 times 2 amps must be negative 10, all right? And that's going to be negative 20, which is going to push a 10 on the other side. So that's going to be 15 I2 is equal to positive 10, or that I2 is 10 over 15 amps, which of course reduces to 2/3 amps, or you could write that as 0.67 amps. So you'll have 2/3 amps going through this part of the mesh, okay? Where you have 2 amps here, you'll have 2/3 amps going there, okay? So that's not too bad. Paying attention to the fact that there's no work to do to find a mesh current where you have a current source here provided, okay? So let's consider a little bit more complicated one, all right? So if we keep moving down on page 63, we're gonna move on to the next problem. This one's a little bit more complicated. And notice in this case that we cannot write a KVL equation for mesh 1. So again, here's mesh 1 down here. Why can't we do that? Because as I indicated before, we can't assume that the voltage across this current source is 0. We don't know what it is. It's not predetermined, okay? So we need to avoid it. If we're going to do KVL, we have to produce voltages. So you don't want to be using this current source to try to figure its voltage out, all right? So what we'll do is we'll define a super mesh to avoid it. And what we need to do is avoid it by just going around. So we'll just sort of sketch here, sort of a dotted line. We'll just go around it completely. And that loop there will define us a super mesh, okay? Again, it's the best way to avoid it altogether. Go around the exterior with those resistances and that voltage source, okay? So let's just go ahead and write what that equation would be. Let's push this up a little bit. Again, our goal is to get these mesh currents, okay? So, so let's do the KVL on the super mesh. And let's do it clockwise. So we indicate the direction we're doing it, okay? So use the mesh currents as we go around. We're going around clockwise. Let's say we're coming through the 1 ohm resistance here. The only current going through that is I1, so you would have 1 times I1. Then you're coming into the 2 ohm resistance. You have 2 different mesh currents represented flowing through it, but we're assuming clockwise, so we're going to assume whoever's in the direction of going clockwise here will be the positive one. So in this case, it'll be I1, and we'll subtract I2. Again, that's why it was important to indicate the direction of KVL. So if we're going this direction, I1 is in the same direction, so it's positive. I wrote I1. I wrote I2 there. I should have written I3, shouldn't I? Yes. Sorry about that. Because this is the current share there, right? And so if we had done KVL counterclockwise, it'd be, it would be a different result, because then we would be, in this case, we would be going in the direction of I3 and not I1. So it just reverses, and so the direction matters. Continuing on, we're coming into the 4 ohm resistance, and again, let's figure out what should we write for the current representation through it. Well, you're coming in this direction. Who's in the right direction? Who's coming into this? If this was the positive polarity, it looks like I2 is, right? So, and I3 is opposing, so it'll be I2 minus I3. Okay, and that should make sense because these two are going the same direction, I1 and I2. And then we come into the the positive polarity of the 10 volt voltage source there, and so we'll add plus 10 equals 0. Okay, so there's the KVL equation there. If we're trying to solve for these mesh currents, we need 3 equations to work for us. So let's do another one. Again, we're just setting up equations. We would need, let's say let's do mesh 3, the one up the top. Stay away from that current source. So let's do mesh 3. Okay, and let's go clockwise again. Okay, and so if we do that clockwise, then of course we're getting, let's start at the top, we'll have 3 times I3 plus coming down here 4 times, let's see, can you do that? Again, if you're assuming PRC for this mesh, right, then I3 is in the right direction, I2 isn't, so it'd be I3 minus I2. Then you would come into the 2 ohm resistance, I3 is in the right direction, but I1 is not, so it'd be I3 minus I1. And that would be equal to 0. So you would have 2 solid equations now. All of them, both of them involve all 3 mesh currents, that's fine. Simplifying them, of course. But the point of looking at the current source there, we know something, right? We know something about how to represent this current source in terms of the mesh current. So that's the question. How can we represent the 5 amp current source in terms of our mesh currents? And the answer is in the same way, exactly the same way we determined what the current would be through a resistance when it is used in in more than one mesh. So in this case, who's in the direction of the 5 amp current source? Well, looks like it's I2, not I1. I1 is rotating and it's opposing it. I2 is following the same direction. So in this case, what we'd simply have is really 5 amps is just I2 minus I1, okay? All right. So we are exploiting that current source saddled between our mesh currents. So I'm giving you good examples of scenarios that can happen. So when this situation happens, this is the best thing to do because now you have 3 equations to work with. Now, granted, this last equation is very simple, but that is enough to set up a linear system, a matrix equation, to solve for I1 and I2 and I3, okay? So we could say these 3 equations are sufficient, and they're linearly independent too, to determine all 3 mesh currents. Okay. Right. I'm not going to set up the matrix equation for this problem, because that's just now just a linear algebra problem. But the goal was to figure out how to exploit that current source. Again, just in review, when we're doing KVLs, totally avoid it because we can't represent its voltage, so that won't help us. But exploit its presence in when it sandwiches 2 mesh currents in this way. Okay. So let's go on to the section 4.2 quickly. It's very similar. The only difference now is what happens if the sources are dependent. In other words, so what we're looking at is when the circuit, as indicated here on the top of page 64, when the circuit has a control source, you simply want to try to express it in terms of the mesh current variables. That's your goal. Just like we did for the independent one a minute ago, getting the 5 amps represented as the difference between those mesh currents 2 and 1, right? So in this circuit, you've got 2 mesh currents, and here is a dependent current source. It's depending on a voltage through the 2 ohm resistance over there, okay? And our goal is to figure out what the 2 mesh currents are so that we could use them to determine all the voltages that we need everywhere. And we're going to assume that the gain parameter here is a quarter Siemens, okay? It has to be Siemens because you're using volts to produce current. So you're going to have to divide out that volt factor, and it's going to have to be amps per volt. So, okay, so let's do this. All right, so let's think about how to write those KVL equations. Well, just like we did earlier, a good idea might be avoiding a super mesh. Avoiding that current source with a super mesh altogether. So again, the super mesh, we would go all the way around. Okay, so if you just kind of indicating we're just going all the way there around the exterior, that will be our super mesh. And avoid that dependent source and get an equation that's got a representation of voltages using current, mesh currents. Okay, so Kvl Super Mesh. We should be getting really good at this. And let's just, let's go clockwise. Okay. So if we're doing KVL and we're doing the Super Mesh and we're going clockwise, let's start off by saying, all right, we would come, if we're going clockwise around this, looking at voltages, we're coming in the negative polarity of this voltage source, so like minus 20, plus what, 4 resistance times the current through it, which has got to be the mesh current I1. Then we're coming over to the 6, but the only current represented for it would be I2. And then we come down here to the 2 ohm resistance, and again, it's just I2. So we get a really simple equation here out of this. So we just sort of clean this up a little bit. We have 4 times I1 plus 6 plus 2 is 8, I2 equals 20. Really nice equation there, okay? So we have one equation, okay? All we need is another one. If there's only 2 mesh currents, you only need a 2x2 linear system. You only need 2 equations, okay? If you have 3 mesh currents, then you need 3 equations, right? So, but we're gonna play the same game, that this current source is sandwiched between these 2 mesh currents, isn't it? Even though it's dependent, but I know what the gain parameter is, okay? So we know that A times Vx, right, with the gain parameter being 0.25 Vx, must be what? Look at the direction of that current source. Who's in the right direction of it? Same direction. I2 is and I1 is opposing. So it really is that differential then, based on how we define mesh currents, okay? We also know from Ohm's law, we know that Vx has to be what? Well, from Ohm's law, that voltage over there through that 2 ohm resistance is going to have to be 2 times I2, isn't it? Yeah, well, that's just Ohm's law. Because the mesh currents are representing, for that particular mesh, what current's flowing through everything in series there, okay? All right, so what we have is the following. We can make some substitutions now. So what we can say is that, well, what we really have is I've eliminated Vx altogether by using the 2 times I2 substitution. So therefore, to get another equation involving just I1 and I2, we have 0.25 times 2 times I2, because that's what Vx is, and that has to be equal to the differential, doesn't it? So a couple of things in play. We have to get this current totally in terms of this dependent current, totally in terms of the mesh current. So no Vx terms can be remaining. And we've done that because of Ohm's law, right? So cleaning this up a little bit, again, that's 1/4 over, that's 1/4 times 2. So you're gonna end up getting I2 over 2, right? Has to be I2 minus I1. And you can clean that up a little bit and should be able to show that what you're going to get is 2 times I1 minus I2 equals 0. Okay, just multiplying through by 2 and cleaning things up a little bit, right? So we have this 2 equations then. What we have to solve then is 4I1 plus 8I2 must be equal to 20 from the KVL equation above. And we've just shown that we have to have 2I1 minus I2, and that has to be equal to 0, okay? So one thing you can do solving 2x2 linear systems is, again, I could write a matrix equation, but if I can always add and subtract these equations and preserve the solution. So I'll leave the first equation below alone. And what I'll do is I'll multiply through, let's just say I'll multiply through by -2 times this equation right here. If I go -2 times all of that, I would get a -4I1, and I would get a plus 2I2, and still 0, right? And then what you can do is add those two. And if we add the 2 equations, you would get 10I2 equals 20. So in fact, the second mesh current is nothing but 2 amps. And if I2 is 2 amps, can you tell me what I1 would be? Is there a relationship we can exploit? Absolutely, right? We know that from this relation up, either equation we could use. Once you know 2, you could use either of them, but I would just probably just say, well, therefore, I know that this differential, I know that half of I2 has to be this, or 2 times I1 is, or that I2 is equal to twice it. So since 2I1 minus I2 equals 0, which implies 2I1 has to be equal to I2, right? Then that just says that I1 has to be 1/2 of I2. So therefore, I1 must be 1 amp. Okay. So in fact, this mesh current is 1 amp. This mesh current is 2 amps. Again, avoiding the dependency completely to get one equation involving the mesh currents, and then exploiting the fact that the source could be represented directly as mesh currents, and then finding a relationship to get rid of that that voltage controlled component of the current source, because we can't leave a Vx term in there. I mean, we have to know what it is in terms of the mesh currents. So you have to get everything in terms of a mesh current somehow, right? Let's solve 2 more problems very quickly, just to get some more experience with this concept of exploiting sources within the mesh current process. Very simple example again, 2 mesh currents, and what you have is a voltage source here and a current source, right? So, so in this case, let's look over here on the right. Can you tell me what I2 must be then? On that side of the circuit, I've represented the reference direction of the mesh current is clockwise, but we have a current source that looks like it's going what? Anti-clockwise or counterclockwise. So I would hope you would say that, oh, in this case, it just means that I2 is minus 1 amps. Exactly. If we happen to write the mesh currents the other direction, it would have been 1 amp. But our convention, remember, is clockwise. So just remember that. That's our convention for mesh currents, is to position them clockwise, right? But this will be handy information. Let's look at mesh 1 is perfectly fine. For voltages, I can handle a voltage source, no problem. Can't do anything about voltage sources involving current sources, but this voltage source up there, 10 volts, is just fine. So if we did a KVL mesh 1, let's do that. For going, let's just say clockwise. And starting up here, we'd come into the negative polarity of the source itself, so you get a minus 10. We would then go through the 5 ohm resistance, which is shared by 2 mesh currents. Who's in the, assuming PRC, who's in that direction? Looks like I1 is, and so then we'll subtract off I2. And then you'll go through the 10 ohm resistance only with the I1 mesh current and set that equal to 0. Again, collect some terms. You can pull the 10 over to the other side. You're going to end up with 15 times I1 and just minus 5, right? I2, and that will equal to 10. Okay, very nice equation. Okay, but we already know this information there. We already know what I2 is. So therefore, 15 times I1 minus 5 times negative 1 must be equal to 10, right? So that tells us that 15 I1, this will be a positive 5, subtracts over from the other side, so you'll get 5. So therefore, I1 must be 1/3 amps. Or you could write it as 0.3, repeating 3 amps, okay? The goal of the problem, though, was actually to find this current just through that resistance. So we have to be careful what we're asked for. Yes, we did find the mesh currents, absolutely. That's one of them, and this is the other one, right? But we were supposed to represent what the current is going through the 5 ohm resistance. And we assume because of that direction arrow, downward, okay? That's important. What reference direction is being used? Because the reference direction being used means downward, again, I1 is in that direction, correct? So therefore, I sub A is I1 minus I2. So in this case, we're going to get a third, 0.33, right? Minus the minus 1, so it'll be 1 1/3 amps, okay? Just for the sake of the argument, if the reference direction for the current had been this direction, right? Just saying, if that had been the case, then what you would have done is you would have said, no, it's the other way. It's I2 minus I1. And that would have meant, in this case, it would have been -1 minus a third, 0.33, and you would get -1.3 amps, okay? Which should make sense. The magnitude is the same. It's just that you'd be opposite in the direction, okay? The fact that this is, the other one is positive indicates that is the correct direction that you should be going through that resistance to get, especially with this current source coming up like this. It will be coming up and then splitting out that way, okay? Okay. All right, so that's awesome. And let's do one more example. Probably a little bit more complicated, but it does have a couple of interesting things to pay attention to. Dependent voltage source, independent current source. Exploit that, but the goal is this current right here. That's what we want. We want the current through the 5 ohm resistance, okay? Right? So if we look immediately where the current source that's independent occurs, I would hope you would immediately, and that would immediately indicate for you that we know I1 is equal to 3 amps. Right? What else do you know? Just for the fact that this is a planar network and we've written the mesh current here, what can you say between the relationship between this current here and the mesh current? Well, because this is a closed path here and this is a planar network and we're defining just through this series of elements here, well, that I1, so also we know, excuse me, that IY must be I3. All the currents through all the elements in this mesh are I1. All the currents in this mesh are I2. All the currents in this mesh are I3. That's the beauty of using mesh currents, okay? So all we have to do is find I3 to answer the question, right? So let's start off with building some equations here that we can work with. So one thing is to think about, I just want to represent voltages through resistances and avoid sources like we did before. So a really nice thing to do might be a super mesh that looks something like this, right? Let's just go around the perimeter of this and stay away from the two sources altogether, okay? So that'll be our super mesh. Avoid those sources, especially since this is dependent upon that current there. So let's do KVL clockwise super mesh. Okay, doesn't matter where you start. Let's start with this 10 ohm resistance. If we're going to represent that voltage, we got to see what current's flowing through it. Well, you have two of them. Looks like I3 is in the right direction, I1 opposes. So you're going to have 10 times I3 minus I1. Then you're going to come up through the 5 ohm resistance with that I3 mesh current, correct? Then you're going to come down to this 5 ohm resistance, which only involves this mesh current. So you have plus 5 times I2. And then you're going to come through this 2 ohm resistance, which is saddled between these two meshes. Assuming PRC, looks like I2 is in the right direction and I1 opposes, okay? And that has to be equal to 0, right? So we have totally avoided that controlled voltage source altogether, right? We can clean this up a little bit with a little algebra. It doesn't, it's not too difficult to exploit the fact that I1 has to be 3, but maybe before we do that, we can simplify this a little bit. And so what we're going to have is 10I3, right, minus 10I1 plus 5I3 plus 5I2 plus 2I2 minus 2I1 has to be equal to 0, okay? Collect some terms here. This says, again, just doing algebra here, 15 times I3, right? Collect the I2 terms. I have 7, right? Plus 7 times I2. And then you're going to have with I1, let's see, a negative 10, negative 2 minus 12 times I1 is equal to 0, okay? But now we can substitute what we know about I1 right here. We know that this is equal to 3, okay? So we have a nice equation now. That means 15 times I3 plus 7 times I2 is going to end up being 36, because that'll be negative 36 to the other side. Nice equation. Boy, if we know what I2 is, we're done, because our goal is get I3, because that current that we're seeking is the same as that mesh current, okay? So we need another representation of voltage with meshes. So let's do Kvl Mesh 2. And hopefully we can get that parameter, this controlled, this gain parameter in terms of our mesh currents, right? So if we, again, go clockwise around mesh 2 down here, let's start with the 2 ohm resistance. You would have, again, let's keep in mind, we have this equation already. We're looking for another one. So if we go through that 2 ohm resistance, let's see, we're in this mesh down here, just this bottom square, right? So you will be in, if assuming PRC, I2 is going to produce a positive value, I1 opposes, so we'll have I2 minus I1. Then we will come into the positive polarity of that voltage source, so we'll have plus, we'll just go and write it, A times IY. And then we're going to come down into the 5 ohm resistance only with that mesh current, so plus 5 times I2, and that has to be equal to 0. We already know what I1 is, so we can substitute that as what, minus 3. And we already know that the gain parameter is 2 plus 2. And we already know that IY has another name. Yes, it's I3. So we are using that relationship there. Then plus I2 equals 0, okay? So we're looking good now, because now we could tease out a completely new equation involving I2 and I3. And we should be getting out of this, let's see, 7I2. Look at the I3s, it's going to stay the 2 plus 2I3, and you're going to have a negative 6 there, and that'll pull the other side. And there we go. Another equation, right? Let's solve this. This is not too bad. So what we'll do is we'll just let's flip this one around here and live it and put things in order. So the first equation is 7 times I2 plus 15 I3 equals 36. The next equation is 7I2 plus 2I3 equals 6. And you can preserve the solution by adding them, or in this case, subtracting them. If we subtract them, that's why we like this. It wipes out the I2 term. 15 minus 2 will give you 13 I3. And 36 minus 6 gives you 30. So I3 must therefore be 30 over 13 amps. Taking your calculator out, it's about 2.307 amps. And by definition, that's equal to I sub A as well. So the current flowing through the 5 ohm resistance up there is really 2.307 amps. So again, just reviewing, using super meshes can give us very nice equations involving the mesh currents, avoiding any dependencies there. And then taking other meshes where we know we can, if we didn't know what that Y was, we would be in trouble here. But we immediately know if this voltage is being controlled by that current, we have a representation of it with the mesh current I3, okay? So just trying to get everything you can involving the mesh currents one way or another is the technique for handling current sources and voltage and current sources and controlled sources.